Hi, this is Sun Jae-yong, and I'm this week's presenter of TEAM4. Before we get started, I'll preview our presentation of this week roughly. Firstly, we're going to talk about the problems coming from lateral force and frequency, which includes earthquake and wind pressure. And then we'll show you how one World Trade Center can hold those pressures. Our bridge is shaking absurdly. The reason why the bridge swings in the wind that even a man can walk is due to its natural frequency. Any building has a natural frequency. The vibration that reaches the natural frequency by the resonant phenomenon causes the building to shake even more. When the building cannot withstand the lateral pressure, the building finally collapses. The high-rise buildings are prepared for wind and earthquakes so that the building do not collapse. The reason of the skyscraper's collapse by these factors is essentially the same. It's because of the vibrations that I've mentioned earlier. Earthquake causes vibration in the ground of buildings. As shown in the video, when an earthquake occurs, the building vibrates. And I'll show you the process of collapse in detail. The building initially holds out with inertia, then moves the same as the vibration frequency increases, and the walls or pillars of the building cannot withstand the lateral pressure caused by vibration, then they collapse. However, the fact that a building is shaken by the vibration is not in itself evidence that it is not earthquake safe. Rather, a well-shakeable building is a safer structure that withstands earthquakes better. This video shows skyscraper in Shinjuku, Tokyo, where vibration was transmitted during the 2011 Tohoku earthquake. As you can see, the buildings shake side by side as if they are dancing. This is not a poorly built building, but rather a well-designed seismic building. And the building is designed to shake flexibly and naturally according to the vibration. When it comes to how much a building is prepared for the earthquake, it's not a matter of strength, but a matter of flexibility. The same goes for the wind. Each skyscraper has its own frequency. While any such movement may initially be minimal, high winds can create vortices that can match the frequency of the building they are moving around, causing noticeable swaying and shaking motions for those inside. Most buildings withstand irregular wind vibrations. The problem is that the vortex is not a regular wind. As wind moved around the top of those tall structures, vortices were being created in a process known as vortex shedding. This process, much like water flowing downstream, acts differently on obstacles depending on how streamlined they are. In the case of these buildings, the sheer block walls created a bluff obstacle that wind had to flow around. As strong winds moved around these structures, areas of low pressures emerged on the opposite side of them, creating suction forces that pulled at the buildings, causing them to sway back and forth. The tower structure is composed of a hybrid system combining a robust concrete core with a perimeter ductile steel moment frame. The reinforced concrete core wall system at the center of the tower acts as the main spine of the tower, providing support for gravitational loads as well as resistance to wind and seismic forces. The core is approximately square in footprint, with a depth of about 110 feet at the base, large enough to be its own building. It houses mechanical rooms and all means of egress. The core structure is compartmentalized with additional interior shield walls in orthogonal directions. The concrete strength ranges from 8,000 psi to 14,000 psi from the base to the top. As for crumbling, the towers are held up by a steel framework that is elastic enough to take the bending without damage. So it gives the building enough flexibility for safe vibration along frequency of the earthquake. A ductile parameter moment frame system is introduced for redundancy and to further enhance the overall building performance under lateral load. The parameter moment frame wraps around all vertical and sloped parameters, forming a tube system. Along the height of the tower, the anti-prism geometry creates unique structural conditions which necessitated the design and fabrication of special nodal elements using relatively large plating with significant capacity for load transfer. For further enhancement of the lateral load resisting system, the concrete core at the upper conical levels is connected to the parameter columns via a series of multi-level outrigger trusses in both orthogonal directions. During the design of a building, special care is to be taken when considering the wind load. Buildings taller than 10 stories would, for the most part, require extra steel for side-long framework. Also, the One World Trade Center's height and its slenderness imposed stringent demands on the overall strength and stiffness of the structure. The structure has been designed for wind load requirements of IBC 2003 with due consideration of the NYC local wind climate conditions. In order to meet those demands in an economical way, high strength was utilized and it composes the core of the tower. In addition, a series of wind tunnel tests were performed to ascertain a more accurate measurement of wind loading and wind responses of the tower with respect to hurricane wind load effects and human comfort criteria. High-frequency force balance test is used to estimate wind loads and vibration frequency of the building to be utilized in structural design, and to measure vibration acceleration of the building to evaluate serviceability. In the HFFB test, light and rigid model is used to measure wind loads by 6 components. The wind force coefficient is computed by time-dependent force data, and response of the model is evaluated by the spectral model analysis. Aeroelastic model test is suitable for slender, flexible, and dynamically sensitive structure like One World Trade Center. The objective of the aeroelastic model test is to investigate the vortex-induced vibration and aerodynamic instability vibration within range of target wind speed. The aeroelastic model is designed with precisely scaled dynamic properties of the full-scale buildings, which is stiffness, mass, natural frequency, and damping properties of the structural system. Responses are directly measured in the wind tunnel using non-contact displacement meters or accelerometers. And on the next time, We're going to study about overall structure and frame of the building and the facade. That's it for our today's presentation. Thank you for listening.